So our next speaker is Bumin Yenmez. I will let him take it.
Hi, I'm a professor of economics at Washington University in St. Louis. This is a joint work with Hafalir, Fukhito, Kojima, and Koji Yokote. In this project, we're interested in an institution that's hiring from a set of workers or a university admitting a set of students. The institution has two goals. One of them is diversity, and the second one is meritocracy. We provide optimal solutions for the institution. Let's start with a simple example. Let's suppose that there is one university. The university has a capacity of 2, and the university has a preference for diversity. There are 3 applicants, Anne, Bella, and Charlie, and the students are categorized into 2 types, female students and male students. For the sake of the example, let's suppose that the merit ranking is as follows. So Anne is the best student, and then Bella, and then Charlie. These students are all good, and so therefore, the university wants to admit a class of 2 students. That means there are 3 choices for this class. The first class has Anne and Bella, the second one has Anne and Charlie, and the last one has Bella and Charlie. Now, if the preference for diversity is not strong, then perhaps the university should go with the first class that has Anne and Bella because they have the highest merit. However, if the preference for diversity is strong, then Anne and Bella should not be chosen because it's not a diverse class. And there are 2 classes that should be considered. The second, Anne and Charlie, and the third one, Bella and Charlie. Now, these classes only differ in the female students. The first one has Anne, the second one has Bella, and Anne has a higher ranking than Bella. Therefore, even when the preference for diversity is strong, the third class that has Bella and Charlie should never be chosen. So the university should choose from one of these 2, right? So the trade-off between diversity and meritocracy is simple, but it can be very contentious. So you may have heard about the Supreme Court case when the Supreme Court decided that race cannot be used as a criteria for college admissions, even for the sake of diversity. Our goal in this project is to find optimal solutions for an institution that has preferences for diversity. We make a couple of contributions. The first one is we introduce a class of choice rules. Each one maximizes diversity, each one maximizes merit subject to attaining a particular diversity level. We study when desirable properties of choice rules such as path independence, substitutability, and the low aggregate demand are satisfied. We find, using this class of choice rules, we find the diversity merit part of the frontier. So if the institution is not sure what diversity level they want, you can provide them as a couple of choices, all the classes that they can admit on the diversity merit part of the frontier, and they can choose from that. And finally, along the way, we provide 2 novel characterizations of Matroids. So if you're interested in Matroid theory, please do check the paper. I won't talk about these characterizations in this talk. There are a couple of possible applications. I will introduce everything in terms of the college admissions application. Assigning students to schools is another example. Many districts have diversity policies. Public and private hiring is another example. Tech companies and United States government is interested in having a diverse workforce. And finally, some auctions have distributional goals, and this is yet another application of our theory. Let's jump into the model. We're going to assume that there is one university. For example, it could be Washington University, and the university has a set of schools. So you can think of them as colleges within the university or the majors that students are admitted to. For example, it could be the School of Engineering, the School of Arts and Sciences. If all the students are admitted as undecided, then this calligraphic C is just a singleton. Everybody is admitted as a group. There are no departments, there are no majors. The set of students is denoted by calligraphic A. Now, each student has a type. The set of types is denoted by calligraphic tau. In the paper, we're agnostic about what these types mean. It could be anything depending on the application. For example, for a university, a type could be, for example, a female veteran. So I'm a female applicant and I'm a veteran, and that's my type. In other contexts, it could specify your socioeconomic status. It could it could specify your caste. It could specify your race and gender and so on. Now, let's look at how we define merit and diversity. Merit is usually defined as follows: equal to being particularly good or worthy. So we just have to look at one application. Is this application good enough for the university to admit? Right? It's a property of an individual application. We're going to use the matching with contract setting. So a contract is going to be denoted, for example, by X. It's going to specify a student, a school within the university, which school are you applying to, and some terms. The terms can define, for example, financial aid. The set of all contracts is calligraphic X, and now the university is able to rank all the applications. So this is the merit ranking that we're going to use, right? So the school can pairwise compare all of the applications that it receives. Now, even though this is a ranking over individual contracts, we need to compare sets. We can admit class 1 or we can admit class 2. Therefore, we need to extend this to sets of contracts, sets of students. How do we do that? Let's take two sets, X and Y. We enumerate the contracts so that the lower index contracts have higher merit ranking in both sets. We say that set X merit dominates set Y if X has more contracts than Y. And for every I, the ith best contract in X is as good as the ith best contract in Y. Right? So this is a very strong comparison for sets, but it will make our results stronger. What about diversity? How do we define diversity? Well, diversity is defined as the practice or quality of including or involving people from a range of different social and ethnic backgrounds and of different genders, sexual orientations, and so on. So diversity is a property of the whole group, not of individuals. Therefore, the university has to look at the distribution of students at every college, at every major that they have. Right, so we're going to count how many women are in the School of Engineering, how many women are in School of Arts and Sciences, and we're going to put these numbers together. It's going to give us a big vector. So we call that vector distribution, and it will be denoted usually by C. And we may have some feasibility constraints. For example, the School of Engineering cannot have more than 500 students. All the feasibility constraints are going to give us the set of feasible distributions, and that's going to be denoted by uppercase C0. Now, given a set of contracts, give me a class, I can look at the induced distribution. So I can count how many women the school is admitting, how many men, how many students with disabilities, and so on and so forth, right? So that's going to be denoted by C of X. And finally, we can define the diversity index. The diversity index is just a function. Give me the distribution. I plug that into my diversity index. It puts out a number. If the number is higher, we're getting a more diverse set of students. If the number is lower, then we're getting a less diverse set of students. We're making this abstract because we want to get the most general results. And I will show you examples of what kind of F we can use in our paper. Now, our solution concept is a choice rule. Choice rule is one of the most basic primitives of economic theory. Give me a set of contracts. Which ones do you choose? That's a choice rule. The only condition is that the distribution of the chosen set must be feasible. If the School of Engineering cannot admit more than 500 students, that needs to be satisfied. All right, so let me jump into the results. So we identify a class of choice rules. So maximize the merit subject to attaining a diversity level. But first, we start with an extreme member of this class where we lexicographically maximize diversity first, and then merit. So the idea is that given a set of contracts, a set of applications, first find the maximally diverse contracts. So we are maximizing diversity from the available set of students. And then, subject to maximizing diversity, choose students with the highest merit. Of course, in general, this is very hard to implement. So this is computationally, it won't be feasible, and this choice rule is not even well defined yet. So our question is, when is it well defined and when is it well behaved? So to train this, we assume a notion of ordinal concavity. So I will skip this definition. So this is a concavity notion used in discrete optimization literature. It was introduced by Murata and Shiura. They call it semi-strict quasi-natural concavity. But because we can't use that when we're presenting to an economist, we said, okay, let's call it ordinal concavity. Okay. So what are the examples of diversity indices that satisfy ordinal concavity? For example, you can reserve a number of seats at every school for every set of students. We need 5 women, 10 minorities, 2 disabled students, and so on and so forth, at every school within the university. And for every reserved seat that we can fill, the diversity index goes up by 1. So this diversity index satisfies ordinal concavity. Or it could be that for every student that we have, or every type, the marginal diversity goes up by a little, and this is decreasing, right? So this is the more general notion of diversity, and it also satisfies ordinal concavity. In addition, the university may identify some types as minority types, and they may care about the number of minority students in the whole university. So that will also satisfy ordinal concavity. Now, given ordinal concavity or the diversity index, we can formally define our choice rule. Give me a set of applications. First, I maximize diversity. So I look at all possible distributions that I can have, and I find them maximally diverse distributions. And then, in a greedy fashion, I choose students one by one, subject to the constraint that every set of students that I choose along the way can be completed to a diverse set of students at the end. So that's the choice rule. So our first result shows that the diversity choice rule has the desirable properties that we want. First, it maximizes diversity, the outcome for a set of contracts X, maximizes diversity among all subsets. 2, the outcome merit dominates any subset of X that maximizes diversity. So we're doing the lexicographic maximization correctly. And finally, of course, in practice, it's not going to be valuable if you cannot actually implement it. So we show that the outcome can be calculated for every X in polynomial time. So I want to talk about the proof. 2 desirable properties of choice rules. So one of them is called path independence. So this is due to plot. It's slightly stronger than substitutability notion that you may be knowing from the market design literature. And so the path independence property is indeed satisfied as long as the diversity index is ordinally concave. Another desirable property is called the law of aggregate demand. This is due to Hatfield and Milgram. The diversity choice rule does not need to satisfy LAD. So we introduce another notion called size-restricted concavity. Under this additional assumption on the diversity index, the diversity choice rule satisfies the law of aggregate demand as well. And finally, well, you may say that, okay, this is extreme, so we like diversity, but we don't maximize diversity all the time, right? So the institution may say, I want enough diversity, and subject to that, I want to choose the best students. So do we need to define a new choice rule? The answer is no. So what you have to do is you have to modify the diversity index. If lambda is the diversity level that the university wants, cap the diversity index at lambda, and apply the diversity choice rule for this modified diversity index. And it will find a solution of maximizing the diversity, maximizing merit subject to attaining a diversity level of lambda. Okay. Now, so this gives the whole class that we want. It is parameterized by the diversity level that you want. Using this class, you can define a new algorithm that we call trace algorithm. And the trace algorithm gives us the diversity merit Pareto frontier. Give me the set of applications. The university is not sure what level of diversity that they want. We're going to provide them with the Pareto frontier in terms of the two objectives, diversity and meritocracy. Unfortunately, this is not guaranteed to be pseudo-polynomial, polynomial, but it is indeed pseudo-polynomial. So this is the related literature. In a companion paper, we show that ordinal concavity and size-restricted concavity are actually needed if you want those two properties of the choice rule. Imamura provides axioms on choice rules based on merit and diversity, and he characterizes choice rules that have reserved and quotas. I think I'm out of time, so that's it.
We can take one question while we switch speakers.
You were projecting this one.